Bonding in coordinate compounds. See, we have very many number of unanswered questions, like we wanted to know always that how the bonds in these coordinates compounds are having a directional properties because of which they acquire different shapes and structures. What exactly is the nature of the bonding is, what exactly how they attain the optical the color and the magnetic behavior, and what how the exactly is the formation of these compounds takes place. So these are all many unanswered questions which we always wanted to know. And the first theory which came into existence, which explained after the Warner's theory's failure, was the valence bond theory. Valence bond theory. We call it VBT. See, this theory has tried, basically it's the same thing which what we have done in the class 11. It has tried to explain the formation of the coordinate compounds as we have done we have given what we have studied in the class 11 to explain the formation of the inorganic and organic molecular species. But here what we have done is we have done slight modifications. The modifications has been done in order to we have what we this VBT is based on the magnetic moment data of the coordination compounds. So as per this theory, we first try to find out what the magnetic moment data of the coordinate compound, and then we say, when we try to predict whether the pairing of the electrons is taking place or not. What the theory says, that whenever a ligand approaches a metal ion, the metal ion's electrons either they uses their inner n-1d orbitals or nd orbitals, they may get paired up or they remains unpaired, and the coming electrons of the electron pairs of the ligands can be accommodated either on these n-1d orbitals, or they may be actually accommodated in the empty nd orbitals. So in that way the sp-d orbitals and different combinations are used, and accordingly different structures are actually of these coordination compounds are formed. Now whether the pairing of the electrons is taking place or not, or whether there is no pairing of the electron taking place, that all depends on the strength of the ligands coming, and that is being predicted as per this theory on the basis of their magnetic moment data. Now let me explain you this example by taking the example of this compound, which is hexaamine cobalt 3. Now in this case, cobalt is in 3+ state, so it is already in 3d6 4s0 configuration. So cobalt plus 3 in ground state will be almost as like this, 1 2 3 4. So it's like this. So it's 3d6 and 4s0 with no electron in 4p. Now since the magnetic moment data says this compound or this complex to be diamagnetic, this molecular species to be diamagnetic, it means what, the pairing of these 4 unpaired electrons is taking place like this. So what happens is cobalt 3+ in excited state acquires this kind of configuration. These 4 unpaired electrons, they pair them with each other, and this is how we get what, the 2 empty n-1d orbitals, which combines with the other s and p orbitals, because there are 6 ligands are coming. So 1 2 3 4 5 and 6. So these n-1d s and p3, so it is called D2sp3 hybridization or combination takes place. D2sp3 hybridization takes place, because of which the complex will be your octahedral, and since all electrons are paired, it will be diamagnetic as predicted, as obtained from its magnetic moment data. So this is how they explain the formation of these compounds, and the theory says since the ligands are donating a pair of electrons to this central cobalt, the bond formed is a purely coordinate covalent bond, or a dative bond. It's a sigma bond, and that is why this whole coordination entity remains intact as one unit. So this is how we explained it. Let us take another example of we have this one. This is your hexafluorido ferrate 3. In this case, what we find is Fe is in 3+ state, so it is already 3d5 4s0. Now what we find is this 3d Fe plus 3 in ground state is having a configuration in the box diagram represented as such like this. So we have 5 unpaired electrons, S and P are empty, 4s and 4p are empty. Now what happens is, see, we again have to rely on the magnetic moment data as per this theory, and the theory says that the magnetic moment data says it is paramagnetic in nature. What does it mean is, let us take, let me give you another example. Let us take 4 minus here, not 3 minus, so it will, no confusion will be there, because even if like this will be 2 plus, so it will be 6, so you make it this one. Because why I have changed it? Because even if there's a pairing of the 5 electrons takes place, 1 electron remains unpaired. Because of that, it can be it can be paramagnetic. So I have completely removed that situation. I have taken Fe in this complex in the +2 state. So in +2 state is having 3d6 4s0 configuration. So in this case, Fe +2 is having 3d6 4s0 4p0 configuration. Now you can clearly imagine, if the pairing takes place, this whole 6 electrons will pair up to form 3 pairs, so there will be no unpaired electrons, so it has to be diamagnetic. But since the magnetic moment data says it is paramagnetic, what does it suggest? It suggests that no pairing of the electron is taking place. So what happens is, where these 6 fluorides are going, they are going into the other empty sp and d orbitals. We know that there is another 4d available, which is completely empty. So what happens is, Fe +2 in excited state is written like this. So this 3d6 remains as such, 4s, 4p, this is 4d. So 6 fluorides, 1, 2, 3, 4, 5 and 6. This is how they occupy these 6 orbitals. So the hybridization formed is sp3d2. Now in this case, it will again be an octahedral complex, but since 4 electrons, these remains unpaired, so it exactly correlates with what the magnetic moment data we have got. Yes, it is found to be paramagnetic in nature. Now this is also octahedral. Then how it is different from the previous example which we have done? The two basic differences what we find is that the other example we are having D2sp3 hybridization. In this we are having sp3d2 hybridization. Both are called octahedral. So what difference you find is, first, that the D in this case comes first, in this it comes in the end. So it is basically, in this case, n-1 d orbitals are involved, in this case n d orbitals are involved. Another example, in these the pairing of the electrons takes place, in these no pairing of the electrons takes place. We call the ligands which form these kind of complexes as strong ligands. We call these type of ligands which form these type of complexes as weak ligands. Then what happens, most important, and since in these cases, in this one where n-1 d orbitals are used, since all electrons pairing of the electrons takes place, these are called they will be having hardly any electron left unpaired, so they are called low spin complexes, inner octahedral complexes. We specifically give them the name inner octahedral complexes because n-1 d inner orbitals are used. Now in these cases, a lot of unpaired electrons are left out as such, as I have explained here, so they will be having very high spin, magnetic spin. So they are called high spin complexes or high spin outer octahedral complexes, because the d orbitals involved are nd orbitals. So this is how we have two types of octahedral complexes, inner and outer.